Hello everyone. Today we are going to see the crash course on aldehyde, ketones and carboxylic acids. Particularly today we are going to deal with aldehyde and ketones alone. In the next video we will see in detail about carboxylic acids. So there are some similarities in these three functional groups, which is these are having carbonyl groups in its functional group formula. For example, aldehyde, that is having CHO, ketones, that is RC double bond OR, and carboxylic acids, that is RCOOH. So all three which is having C double bond O in common. So let's get started what we are going to see in today's session. We are going to start with the nomenclature, structure, isomerism and physical properties. Also electrophilic and nucleophilic addition reactions, aromatic aldehydes and aliphatic ketones, aromatic ketones also we are going to see. How to convert aldehydes to ketones and carboxylic acid, these three conversions, and most importantly we are going to see about the mechanisms of named reactions which covers in this chapter. For example, Aldol, Cannizzaro reaction, fissure esterification and much more. So without any further delay, let's get started. First, let's start with a simple nomenclature. We know this one as formaldehyde, which is also known as methanal. So aldehyde groups must be end with the name ale. Okay, so what about kind of difficult one? Aromatic ring, which is having CHO 2 times. What is the name of this aldehyde? We must have encountered the carboxylic group attached to benzene ring, but not the aldehyde group. This is called phthalaldehyde. If carboxylic group is attached to it, then that is called as phthalic acid. What about the IUPAC name? This is 1,2 benzene 1,2 dicarbaldehyde. Okay, what about ketones? Let me take a ketone like this. What about this? It is having a double bond as well as keto group. This ketone is called mesetyl oxide. I'm telling you the famous and also the questions can be asked from this part. So I don't want to go into the simple ones which you know already. This is mesetyl oxide. IUPAC name 4-methyl, because ketone is a functional group which gets more priority. So 1, 2, 3, 4, 5. So 4-methyl pent 3-ene. Third position I'm having double bond. So 3-ene 2-one. Second position I'm having ketone group 3-ene 2-one. Okay, cool. So let's talk about this nature of the carbonyl group. How it is a nucleophile or an electrophile, how the hybridization happens. I told you this group which is common in aldehyde, ketone and other carboxylic acid as well. This is called carbonyl carbon, which is sp2 hybridized. It is having sigma bonds and pi bond with oxygen. More importantly, this is polarized because of the electronegativity difference. Oxygen, that is more electronegative, and carbon, that is less electronegative than oxygen. So the bond is polarized. This is why lots and lots of reactions happens through this functional group. Let's prepare it first. Let's see the preparation. First method, the well-known method, is from alcohol. By what? Oxidation. Oxidation of alcohols. I already told you, if you are oxidizing primary alcohol, you will end up with aldehyde with the same number of carbon, and if you are oxidizing the secondary alcohol, then you will get ketone. Okay. Here, point to be noted is you have to use the mild oxidizing agent like PCC, PDC, or chromic oxide. In case of chromic oxide, I want to tell you an important point. Chromic oxide, which is also known as John's reagent, which is for the oxidation of secondary alcohols only. What if I am adding primary alcohol to this reagent? What will happen? It will get oxidized to formation of carboxylic acid. Okay, so if you want to stop with the a carbonyl group like aldehyde, this method, this reagent is not suitable for that. But if you want to create ketone from secondary alcohol, you can choose this John's reagent. Okay, the second method, that is hydrogenation of acid chloride. Hydrogenation of acid chloride. Acid chloride functional group is RCOCl. So if I am doing hydrogenation over here, in the presence of palladium and barium sulfate, it will give you aldehyde. This is the most important named reaction, that is called as Rosenmund reduction. The question can be asked in this part is that what is the duty of palladium here? That is a catalyst. What is the duty of barium sulfate here? That is poisonous catalyst. What is poisonous catalyst? That decreases the speed of the reaction, decreases the rate of the reaction. Catalysts are the one which can speed up the process, which can alter. The most apt definition for catalyst is that which can alter the speed of the reaction or rate of the reaction. In that, the poisonous catalyst decreases the activity. Okay, this is super important name reaction. Okay, then the third preparation part is the distillation, dry distillation, by using what? Calcium salt. I am taking RCOO twice with that calcium salt. When I am using twice of this, or if I am taking another calcium salt, doing distillation, what will I get? I'll be ended up with calcium carbonate release and RCHO. What if I'm taking the same salt? which will be written as like this, is it? Calcium. I'm taking 2 moles of the same calcium salt, doing the distillation. Same thing happens over here with the elimination of calcium carbonate. If calcium carbonate is getting eliminated, for example, let's say calcium and 3 oxygens, remaining what will be there? HCHO. That is the product, HCHO. Okay, just to eliminate the calcium carbonate and write the remaining product. You can take any groups. Instead of R, you can put any groups. Okay, the fourth preparation is that from alkene. Let's say that the simplest alkene I would take ethene with carbon monoxide and H2 in the presence of a complex, that is cobalt complex, cobalt carbonyl complex, which will produce CH3CH2CHO. You can see whatever the alkane I just took, 1 carbon extra from that alkene. Okay, so that kind of aldehyde is forming. This process is called oxo process, and there is another method from alkene itself, that is CH2CH2 with palladium chloride with water. It is producing the same number of carbons, CH3, CH4. This process is Wacker's method. Okay, these two methods are also important, oxo process and Wacker's method from alkene. Cool. So what about aromatic aldehyde? That is so simple. If you are taking C6H6 benzene with carbon monoxide and HCl in the presence of anhydrous AlCl3, so which will give you C6H5CHO. The important part is the name of this method, which is Cattleman-Koch synthesis. Don't get confused with our Cattleman reaction we saw about benzene diazonium salt. That is not this. This is Cattleman-Koch synthesis. I told you why we are using aluminium chloride, because that will act as a to prepare the electrophile. Aluminium chloride empty orbital will be used. The next method to prepare aromatic aldehyde is that Cattleman aldehyde synthesis, where we are using benzene with HCN and HCl. Same thing, anhydrous AlCl3, which is producing C6H5CHO. This is Cattleman aldehyde synthesis. Sorry. Okay. So, is there any other method to prepare aldehyde? Yes, we do. The important method from dihalide, RCS2R. aqueous NaOH. It is producing RCOR. Also, you can reduce carboxylic acid to prepare aldehyde, which is, let's say I'm taking carboxylic acid. Two moles in the presence of manganese oxide, that will give you carbon dioxide, which ketone. And what if I want an aldehyde then? In place of R, I am using H. In that case, I'll be ended up with CO2 with R C double bond OH. That is aldehyde. Okay. Other methods, you can go through ozonolysis. Ozonolysis, I have told you, if I am taking alkenes, what I have to do? Break the double bond, put double bond O. The rest, keep it as such. That's it. The other method, phenol-phenolone rearrangement, which would be rarely asked, but I am going to give you that method as well. CH3 COH, which is a diol. Diol, that is going to give us a ketone. By the names mentions, that is pinacol, oil, so which is alcohol. That is giving us pinacolone, ketone. Here, rearrangement happens of CH3 group and so many things, but I don't want to get into those things here. The process is from diol, in the presence of acid catalyst, I am getting ketone. It's depend on your reactant. That's more important. Then finally, Stephen's reaction. What is this? From cyanide or nitride. Remember the catalyst SnCl2, HCl and ether. In case of named reactions, please remember the catalyst. Unlike other reactions, we can't put the random catalyst in case of named reactions. So here I can give you a trick. Stephen starts with S. We know that reduction is going to happen, so SnCl2, and which ends with N, so Cn, that is a reactant, which is going to give us R C double bond O N H. Upon further processes, I will lead up to C double bond O with H, and then ammonia will get released. Stephen reaction is particularly for aldehyde, presence of tin chloride, HCl. Okay, so let's see with Grignard reagent as well. We already discussed about that, is it? So if I'm taking RCN with RMGPR, it is giving us RC. This goes as plus, this goes as minus. So the group R will get attached over here, and the remaining ones are double bond N, Mg, Pr. Hydrolysis will happen. So R, Cr, double bond O with ammonia and then Mg, yes. That's it about the preparation of aldehydes and ketones. Let's see the properties. Methanol is gaseous state, and in case of ethanol that would be a volatile liquid. But the other aldehydes and ketones are liquid to solid category at room temperature. Comparing the boiling points of aldehyde and ketone. Ketones are usually, this will be more boiling point than hydrocarbons and ethers, of course. If I am comparing the boiling point of aldehyde and ketone, for example, if I am taking propanol, the boiling point is 322 Kelvin, and if I am taking methoxyethane, the boiling point is 8281. So as the molecular mass increases, the boiling point is also increases. Please remind that category as well. That applies for all other from groups. And one more thing need to be remembered, this is having higher boiling point than hydrocarbons and ethers, but lower than the alcohols. Okay, because of which this C double bond O group. Let's start with the nucleophilic addition. Nucleophile, we know that is an electron rich species. What is that is attacking our carbonyl group? So if a nucleophile is coming into picture, first will attack over here so that oxygen becomes O minus. Then an electrophile group or any positive group comes into picture, which will neutralize the oxygen. So that is what the general category is that. So what about the other nucleophiles? Let's see some examples. Let's take it with HCl, the strong nucleophile. Cn minus will attack then OH will be formed. Okay, high H plus, that's what I said as an electrophile. So this holds true for aliphatic aldehydes and aliphatic methyl ketones. So what about the nucleophile as sodium bisulfate? OH, then SO3, Na. If I am reacting it with Grignard reagent, what will happen? What is nucleophile here? R minus, and this becomes plus, is it? So R will get attached and remaining OH will be formed. Particularly, if I am taking an amine group, which is NH2, G. G can be of anything. G can be of OH, G can be of NH2, another NH2, or I'm writing the G over here, can be of another NH2 group or OH group, or more importantly 2,4 DNP. Guys, this is super important reagent. Please note it down. 2,4 DNP, or G can be of NHCO NH2, or any aromatic amine as well. So whatever is there which is attached with NH2 group, it becomes C double bond N G. Okay, so if they are more keen to test your knowledge, they may ask you the pH of this particular reaction, which comes out to be 3.5. pH should be 3.5 for these reactions. Okay, that is about the nucleophilic addition. In case of oxidation reactions, we know that already. On oxidation, aldehyde will give carboxylic acid. That's true. Let's say I'm taking the aldehyde. What other reagents can be used to form a carboxylic acid? Yes, we know K2Cr2O7. That is a strong oxidizing agent. Other than that, Tollens reagent, guys. Tollens reagent. You must have heard about this in your practicals as well. And the twin sister or brother of Tollens reagent is that filling solution. If you are keen about what is Tollens reagent, ma'am, Tollens reagent is ammoniacal silver nitrate. Ammoniacal silver nitrate. How it can be written? It is forming a complex like this. Please be noted, here you have to maintain a basic medium to get the silver mirror. Okay, so whenever you are doing a aldehyde test or ketone test in your lab, if an aldehyde is present, it will be positive for aldehyde. What is positive? How we can we'll get to know that is positive? It will show a silver mirror, or in a worst case scenario, it will show a black precipitate also. Okay, so please be careful with this guy, Tollens reagent. Okay, so what about filling solution? Filling solution, we have filling solution as two parts, filling A and filling B. One is copper sulfate pentahydrate, copper sulfate solution. Another one is sodium potassium tartrate. You can use this whenever the examiner is asking questions in your practicals as well. Okay, so sodium potassium tartrate, filling A, and filling B, which is copper sulfate. Why we are mixing it together? Why we are mixing it at the time of reaction only? If the question is asked like that, then your answer should be, if I am mixing it, it will get reacted, lead to the different product that is not needed for the test for carbonyl group. So that's why we are not mixing it. So what would be the positive reaction if aldehyde is present? It will show a red precipitate. What is that red precipitate? What is that silver mirror? I'll explain. So first of all, this is also holds true whenever aldehydes are there, and particularly aliphatic aldehydes are there. Say for example, if I am taking, this can be asked, guys, please be careful. This is ketone, so it will not give positive to Felling's test. This is also aldehyde and this is ketone. So among these two, which will give positive to the Felling's test? Here the point to be noted is this aromatic aldehyde will not give. I told you only the aliphatic aldehyde. What about this? That is having a alpha hydroxy ketone group, correct? This will give positive to Felling's test. How, ma'am? Yes. It will undergo tautomerization to form aldehyde. So that's why this guy is giving positive to the Felling's test. Okay. As I asked you, why red precipitate, why silver mirror, and how that will look like. The tolerance test will give you alpha hydroxy ketones only, and ketones will not give true for this test. What is happening over here is simple oxidation, right? So oxidation which will produce silver as a precipitate. Apart from that, RCOO minus will be formed, carboxylic acid at the end of the oxidation. The silver is responsible for our silver mirror or black precipitate, and oxidation happened. This is as usual, RCOOH will be formed. What about Felling's solution? Felling's solution, again RCOO minus will give. Apart from that, copper 1 oxide is forming as a precipitate. That is what the red precipitate is. Okay. So red precipitate, and what are those categories are formed. So I am once again telling you, Toland's reagent, true for alpha hydroxy ketones, can undergo this test, and aromatic and aliphatic aldehydes. In case of Felling's test, only for the aliphatic aldehydes and alpha hydroxy ketones. Okay, let's move on. Let's move on to the next reaction, that is reduction. Reducing carbonyl group, what that will produce? Let's say I'm using, reducing means nothing but the hydrogen. Hydrogen will coming into picture, palladium hydrogen, nickel hydrogen, or lithium aluminum hydride, or sodium borohydride, right? So in that case, it will give you CHOH in case of carbonyl group. So point to be noted here is, let's say I am taking a acetaldehyde. Okay, so upon reducing it, it will produce CH3 CH2OH. And if I am taking acetone, then upon reduction, it will give you CH3 CHOH. Sorry, CHOH CH3. So this is primary alcohol and this is secondary alcohol. Okay, so please be careful. And what else the reducing can give. What else the reducing agents can be used? That is HI with red phosphorus. That will give you CH2 hydrocarbons. Okay. Another two reductions. I think we have already discussed about this. The first one, Clemmensen reduction. We discussed this in previous videos as well. Clemmensen reduction, the reagent is so important. The reagent is zinc amalgam with acidic medium. Okay, that will give you RCH2R. The second reaction, which is very similar to this, that is Wolff-Kishner reduction. Wolff-Kishner reduction. I am taking the same aldehyde or ketone, which will give you RCH2R, but the reagent, that is hydrazine, NH2 is hydrazine, and the catalyzed reaction is base catalyzed reaction. Okay, so if an carbonyl group is acid sensitive, we have to use Wolff-Kishner reagent to produce hydrocarbons. Okay, then the next reaction, that is polymerization. Polymerization, we very well know about that. What is new in here is, we know the polymerization of hydrocarbons. Here we are talking about aldehydes. I am taking formaldehyde at high temperature 373 Kelvin, which is producing CH2O can. Paraformaldehyde. Okay. Another important reaction is that I am taking 3 moles of acetaldehyde, treating it with concentrated sulfuric acid. The reaction is important. Listen, CH3 which is attached with CHO. That I am writing it as like this. Okay. I am having another CH3, CH4. And I am having oxygen for this as well. Another CH3, CH4. Oxygen. So connect all of these. Metaformaldehyde. Aldehyde. Let me correct the spelling. Aldehyde. This is one of those hypnotic chemical. What if I am having 4 moles of acetaldehyde? In the same, acidic medium is maintained, but here I am using dry HCl. It will lead to the formation of CH3, CHO. Then again CH, CH3. This is having another oxygen. And I am taking another molecule that is also having CH, CH3, O, CH, CH3, Connect all of those. This one is metaldehyde. It is a solid fuel. Now we are entering into the named reactions part. Here I am going to see the first reaction as aldol condensation. Aldol condensation, the important question, first thing you have to understand is that aldehydes and ketones containing alpha hydrogen atom. It should have an alpha hydrogen atom to undergo aldol condensation. So that is an important question. The question is that which of the following can undergo aldol condensation? That kind of simple question can be asked from this part. Okay. So what is formed? What is happening over here? I'm going to tell you with the mechanism. Watch it carefully. First thing first, let me take a simple aldehyde that is having an alpha hydrogen. CH3CHO. 2 moles of aldehyde, and that is undergoing reaction with dilute NaOH. Okay, so the product formed is that CH3CHOH. CH2CHO. It's just a condensation. What is condensation? Eliminating some small molecules and join together. That's what the condensation is. Okay. So this molecule that is having alcohol group as well as aldehyde group. That's why the reaction is called aldol condensation. The name of this product is beta hydroxy butyraldehyde, because 4 carbons are there, no? So beta hydroxy butyraldehyde. Okay, how this happened? Why we are giving so much importance to alpha hydrogen? For that we have to look into mechanism. First step, that is formation of carbanion. Carbanion means what? Which is having a negative charge in it. Right? So I am taking acetaldehyde in a well structured and expanded formula. Formation of carbanion. So what happens? I told you that is a base catalyzed reaction. So whenever I am writing a base catalyzed reaction, OH will come into picture as a first step. So OH will come and attract the H+. So water will be removed, remaining H+. Remaining carbon will possess minus charge. C minus H and CHO. Okay. Will that be stable enough? No. Right. So here I am having a double bond. So it goes like this. Tautomerize or rearrangement happens. C O minus H plus H. So this is what our tautomerized form. But the carbanion is this part. Okay. As a next step, step 2. Attack of carbanion on another aldehyde. We took 2 aldehydes. So attack of carbanion. So people also refer this carbanion as enolate. So don't get confused in that area. Carbanion or attacked by enolate, both are same. So I'm taking another aldehyde. What is here? Our carbanion is here, CH2 minus with CHO. So what will happen? As I told, attack O minus, which will lead to CH3 O minus H CH2 CHO. And step 3. If you didn't understood any of these steps, please mention in the comment. We'll create a separate video with an examples for this. Step 3, that is abstraction of H+. I'm taking a product from step 2. Abstraction of H+. From where this is happening? From water. So from water, it is getting our H+. So it will be formed CH3 COH CH2 CHO. Okay, so this is what our aldol is. Sometimes examiner will give you heat at the end of the reaction. In that case, what will happen? If heat is passed over here, usually if I'm heating something, water particles will get eliminated, isn't it? So here also water will get eliminated. OH from here, another H from here. So which makes it, which will become a double bond system, that is C double bond CH CH CHO. Okay, so this is alpha beta unsaturated aldehyde. The name of this particular product is that croton aldehyde. Croton aldehyde. Okay, so this is what the mechanism of aldol condensation. You can also try it out with different aldehydes. Say for example, you can try it out with CH3 CHO plus CH3 CH2 CHO. If I am taking a different aldehyde, then the reaction is called cross aldol condensation. Okay, cross aldol condensation. Let me know the product in the comments. Okay, our next reaction is that Cannizzaro reaction. This is also very important named reaction. Just opposite in case of conditions. Cannizzaro reaction happens when there is no alpha hydrogens. Alpha hydrogens shouldn't be there. Say for example, C6H5 CHO, where the alpha hydrogens are not there, and undergoing reaction with concentrated NaOH And in case of aldol condensation, I told you it is giving us a condensed product. OH and CHO, upon mentioning heat, you have to eliminate the water to write alpha beta unsaturated aldehyde. Here, remember, this is undergoing disproportionation kind of thing. Say for example, the products are aldehyde. What happens if I am oxidizing it? This will form carboxylic acid. Right? What happens if I am reducing it? It will form alcohol. Right? So these are the products of Cannizzaro reaction. Okay. So let me show you the mechanism of Cannizzaro reactions as well. I'm taking benzaldehyde. As a first step, once again, this is a base catalyzed reaction. So OH attacks C6H5, O minus, H, OH, then again, since I mentioned a concentrated NaOH, in case of high concentration, again one base is getting attacked, this hydrogen, which is leading to the formation of dianion. Dianion. So what is the duty of this dianion then? As a second step, this dianion will react with the another aldehyde, not directly, but the shift is going to happen over here. Shift of this hydrogen as H plus to attack this carbon. So the shift of this H plus, where lift will be C double bond O, O minus, and then the hydrogen is getting shifted over here. So what will happen? This O goes above. So H, C, O minus, C6H5, another H. So once again, with the H plus, but with water, this becomes H, OH, C6H5, and then the sodium, which will be there in the system, that is becomes the sodium salt of carboxylic acid. Okay, so here the rate determining step, always the slow step, that is a rate determining step. So this step is rate determining step and this is slow step. So what would be the rate of the reaction then? So rate of this reaction, which is our benzaldehyde, two benzaldehydes, and also OH minus. So the order becomes 4. Okay. Similarly, if you are taking different aldehydes which are not having any alpha hydrogens, for example, C6H5CHO plus HCHO, that will give you Cannizzaro reacted product, and this reaction is crossed Cannizzaro reaction. Here I can give you the product, don't worry. Only I am asking you to give me the crossed aldol condensed product. Here the products are minus Na plus and C6H5 CH2 OH. Okay, so let's solve the famous question of combining these two reactions. That is the question, this was asked in JEE Advanced 2011 if I am not wrong. CH3 CHO with HCHO in excess. That is giving you, in the presence of concentrated NaOH, A. Question is that X moles of formaldehyde is reacting and Y is the number of OH groups in the product. Very interesting question. OH group in the product. Find X plus Y. That is the question. So very simple and very interesting question. Let's solve this. Let's try to solve it in a minute. CH3CHO, aldehyde is given. It is reacting with formaldehyde. So this is the product will be formed as HCOO minus and Na plus with CH3 CH2 OH. This is Cannizzaro part. Right. Ma'am, you told us alpha hydrogen, no alpha hydrogen must be involved in Cannizzaro reaction. This is a crossed Cannizzaro reaction. Okay. Then, in a question, they have mentioned excess. So, what happens over here is that aldehyde, this aldehyde will undergo the reaction of aldol to form HCH CHO as a enolate. Correct. So what would be attacking our formaldehyde? Which will lead to CHO and then O minus HH. Okay. Will that stop in this part? No. Right? So with water, it will take up the hydrogen to form CH2 CHO and another aldehyde, another two that will be formed as a, just having a alcohol in it. Right? Okay. Once again, I'm mentioning you in the question, they have mentioned that is HCHO in excess. So till I'm having a alpha hydrogen, this reaction proceeds. Here I'm having how many alpha hydrogens with the aldehyde? 2. So 2 more formaldehyde is reacting to form CH2OH, CH2OH, which O will be formed. Now you see all those alpha hydrogens are getting substituted, got as alcohol. But reaction won't stop here because that is mentioned as excess. It is undergoing Cannizzaro again. So Cannizzaro means, of course, oxidation and reduction happens. So this part will become OH, CH2OH, is it? So CH2OH, CH2OH, and again CH2OH. Along with that, formaldehyde as HCOO minus. So this is the end product. Here I am having how many OH groups? 4 OH groups. You can write this fancy stuff as like this. Okay, 4 OH groups. How many moles of formaldehyde is used? Let's take 1, 2 here. So total 3. And then 4. You can't consider this because this is not our end product. So total 4 CH is a formaldehyde and 4 OH groups. The answer is 8. Okay. So this is one of those tricky at the same time important question. And the last reaction of carbonyl group of today, that is condensation of acetone. So I'm taking acetone like we did for aldehydes polymerization. Here I'm taking acetone as 2 moles. In the presence of tri-HCl, mesitile oxide is formed with the elimination of water. Once again, it is reacting with acetone to form a complex or form a compound like this. So here you can see H2 and oxygen leaves us a H2O, CH, double bond, C, CH3, CH3. Here also CH3, CH3 only. That is phono-row. I am reacting 3 acetones with concentrated sulfuric acid. Here I used dry HCl in the previous reaction. Here I am using concentrated sulfuric acid. The reaction like eliminating of water only, but happens which will give you tri-substituted benzene. The name of this product is mesitylene. Okay, so this is about aldehydes and ketone reactions. The important reactions, all of them I have covered. Please go through it. Please do as many as problems you can. We'll see in the next session. Until then, practice more.